Hey guys, what's up? It's Kurt here, and we're going to do a Bernoulli pipe problem. This is something you'd see in a typical mechanical engineer or civil engineering undergrad class, or if you're taking the FE exam for engineering. Okay, let's go through this. We see that we have a converging fitting. In other words, just think about it as just water in a pipe here. You know, it's not exactly a classic uniform cylindrical pipe, but just think about it as just water flowing through a pipe or a hose, like you've seen in your life before. When they say flow is incompressible and friction is negligible, that's just a hint saying, hey, jump to Bernoulli as fast as possible. So I'm going to write out the Bernoulli equation now. It's P1 plus rho 1 V1 squared over 2 plus rho G Z1. And that is equal to its, basically its cousin right here, or I'll call it its brother and sister pair. I don't know what I'm saying when I say brother and sister, but it's exactly the same on the right hand side here, right? It's just the only thing that's changed is the subscript. And that should make sense because what comes in comes out, right? Like the water that comes into here and that goes through this cross section here has to go through that cross section here and come out there, right? Hence, this is location 1 and this is location 2. Okay. Real quick, I just want to make a note here of this problem. They're asking you for gauge pressure. They give you P2 equals P atmosphere here, and that would tell you, like, oh, immediately I should write this guy as P atmosphere. But the actual answer to that is no, this guy should be 0 because they're asking you gauge pressure. So that means ignore, the fact that this is exposed to atmosphere, and they just want to know what it would be as if, like you were that water particle, right here. And they don't really care about its effect in the atmosphere. The atmosphere's effect on that water particle in that instant. Okay. Another quick thing here is we see that this water particle here, well, we call it water parcels, right? It's really just traveling from here to here, right? On that streamline, meaning Z1 is equal to Z2, so then we can cancel out these guys as well. Another quick thing here is that rho 1 is equal to rho 2, right? There's no reason for the fluid's density to be changing. So I'm going to now rewrite the whole equation to something more simple, which is P1 plus rho, and I'm going to try to make my rows more slanted here so it doesn't get confusing. V1 squared over 2 is equal to rho 2 V2 squared, not rho 2, just rho. There we go. So that's our new equation, and this is what we want. However, if you said, hey, Kurt, we need to find P1, but we are missing V2, right? Note that they don't give us V2 around here. And that's just like an unfortunate situation, right? But we can use the fact that the flow rate Q is equal to A1 V1 and is equal to A2 V2. This is, very standard case, and you can think about it this way, right? If you had your finger on a hose, right? Like that water has to go through that hose. And if the hose was, longer, I mean not longer, if the hose was wide, right? That water slows down. But then if you squeeze that hose, or in fact put your finger at the end of the hose, that water, shoots out the hose faster. So for us, this A1 is bigger than A2, right? So we have A1 is bigger than A2. And if A1 is bigger than A2 and these guys are equal, that means that V1 is less than V2. So the water is speeding up. Either way, let's just solve this equation and then put it into here, right? And I don't know why I say either way. It's kind of like going to be that way. So V2 is equal to A1 V1 over A2. And that guy is equal to pi over 4 times D1 squared V1 here, pi over 4 D2 squared. And whenever you're dealing with, like, this is circular here and circular here, the pi over 4s always cancel out. And D1 is 150 millimeters. And I should write V1 as well. 1.2 meters per second squared. And then D2 is 75 millimeters. You can see that the millimeters don't cancel out here. And 150 divided by 75 is 2. 2 squared is 4. 4 times 1.2 is 4.8 meters a second. Okay. So now we're going to put this number right into there, right? And then we're going to be done. But I want to clean up the equation a little bit more. So let's write like this. P1 is equal to rho over 2, and that's V2 squared minus V1 squared. And rho is 1,000 kilograms a meter cubed. That's the density of water. That's very standard. Very standard approximation. It's like 998 something, but just write 1,000. It's quick math here. V2 we found to be 4.8 meters a second. And then V1 was given to us at 1.2 meters a second squared. If we put this in our calculator, we get 10,800. And real quick, think about the units here, because they have KPA. They have KPA. We are not going to have KPA unless we convert. So real quick, kilograms over meters cubed, and then we have this times meters squared over seconds squared, right? This is equal to kilograms times meter, not meters. Actually, I'll write it like this. Kilograms, oh my God, I'm messing everything up here with my pen. Kilograms times meters a second squared over meters squared, right? That is the same thing here. And over here, that guy is what? That's mass times acceleration. That's a Newton. And then over meters squared, that's area, right? So that's force over area. And that is in units. That's a pressure. And you describe pressure with pascals here. Okay, I just wanted to verify that for you. It's very important to get your units correct. So now we have 10,800 pascals, and we want this to be in kPa, so we're going to divide it by 1,000, and you get 10.8 kPa. So that is your final answer. And then you'd see that we can now, move on to the next problem. When you're taking these exams and doing exams, you can do it a lot quicker, but I wanted to go through all these problems, all the steps here, right? So if we recap a bit, just think about what you're given and the conditions and what they're asking for. Because if they were asking for the, absolute pressure and not the gauge pressure, we would have not done this as 0, right? And we would have put P atmosphere. So remember the difference between gauge and absolute pressure. Next thing we did is we had to use the fact that the water goes in and then it goes out. As obvious as that sounds, it can get confusing at certain times, but just remember that fact, and then you can find V2 or V1 or A1 or A2, whatever they're not giving you in the problem. And then from there, just put it in one big equation and watch your units before you go. Okay, guys, I hope that helps you, and that is all, and good luck on whatever you're doing.